All right, hello. This is my lab three, beam vibration. Let's get straight into it. All right. Um, our objectives. We're essentially taking a cantilever beam and we're adding different responses to it and finding its response. We're gonna see. We're using a strain gauge and we're gonna measure dynamic tip displacement. Once we get it, we're going to compare it to our theoretical models, then perform a spectrum analysis and determine its natural frequencies. So the setup, we have 3 ohm resistors and we have our fourth resistor in the form of a strain gauge. We're using the MSP 432 for data acquisition and the MATLAB GUI to help us out. The cantilever beam setup, quite simple. We have a 9-inch beam right here, and we also have a reference plane that helps us measure from a parallel point at any point of time. And the third ruler measures our displacement. The setup, so we're going to have an initial displacement scenario. Then we're going to also have one with an impulse by dropping a quarter, 4 inches. And then the last one, we're going to explain our dampening by adding some tape on the underside. All right, strain gauge sensitivity. We get this by taking the voltage out and also the deflection and finding the slope. So I got a sensitivity about 21,000 millivolts per volt. This was well within the accepted scenario. This was within the accepted data, but I wanted to use a more accurate one, so I used 1300 provided by Nowinski, and this made my initial displacement more reflective of everything else. Beam stiffness, we find it by displacement versus force, and I got a slope of this. The K equivalent found by one of the equations in the pre-lab, we get it by this. Close enough. My assumptions made with basic aluminum. And this is going to be helping us construct further models. For our initial displacement, this is our raw voltage that we get directly. This is not calibrated due to the initial strain of the strain gauge when it's just hanging. So what we do is we get the steady state at the end, and then we subtract it from the beginning, and that adjusts our steady state. So it's more accurate now. Then we times our sensitivity by our voltage out, and we get our displacement. I got displacement in inches and millimeters for different variations. All right, if you zoom closely in the data, it turns out that there's a lot of local peaks everywhere. So what we did first, we eliminated the peaks in the middle of the oscillation. All right. Then additionally, this part at the beginning, we also cropped it out so we could have a beautiful line of best fit. Um, in order to do that, what we did was now we get our displacement at one point, and we get it at the other point, and then we this is our then that's how we get zeta by dividing it by the number of terms throughout. Right. What we find is this system is underdamped and the damping ratio is only 0.28, which is underdamped. And this makes sense because oscillations keep happening after in the steady state, probably indefinitely from what the data shows. Our natural frequency and damp frequency are the same essentially because it's just such there's really no damping in our system. And to put it in a single degree freedom equation of motion, um, using our pre-calculated data. Right here, the blue, that is our theoretical data, and the orange here is our experimental data. And as we can see, they look very similar in the shape. Um, it it's a bit more steep, our actual data, but other than that, I think it's a pretty good fit. It matches the same qualities. All right, and then for our spectral analysis, we use a fast Fourier transformation in order to, at the sampling rate of 2000 hertz. We have a decibel scale and a regular scale. As we can see here, around 14 hertz, that's what our natural frequency was. And then when we calculated our own natural frequency, it was 13. So they're very close together. Very happy with the result. So the next one is the impulse. Same story with correcting the voltage by getting the steady state value. And then we can also see our displacement out. Same story with the impulse. Uh, so we actually got three different frequencies, one at 14, one at 90, and one at 250, which is very close to our pre-lab values that we calculated. And then same way we transformed it, but this is our three modes. Very, very happy with this result. Last thing was the dampening. So we put 4 inches strips underneath the cantilever beam in order to add a dampening to it. As we can see, not only does the steady state get smaller, but also approaches the steady state much faster. His steady state was 0.28, and with one of the tapes it was 0.39, and with the carpet it was 0.43. So in summary, we can see that adding the tape increases the damping ratio, but it doesn't increase it as much as it could have, right? It still looks like it's going to oscillate forever, right? Meaning that the damp natural frequency, it's virtually the same. We only get 4 decimal points. They're slightly different. Nothing to like be worried about. But our natural frequency is the exact same because it's the same material under same circumstances essentially. Conclusions, the strain gauge can help us find the natural frequencies of a model. The cantilever beam is an underdamped system, at least the responses scenarios we put it in. And adding a damper will increase the dampening ratio. The cantilever beam is an underdamped system, of course, and a Fourier transformation and spectral analysis can help us find natural frequencies. And these are my references. Thank you.